Today we're going to go over how to do a Monte Carlo simulation for a simple regression model in Stata. This will closely parallel what Bill went over in class, so I'd encourage you to review his lecture notes as well, and also download the accompanying do file that goes with this video. You'll notice at the top, the first line of code sets up a program. This tells Stata that we want to record a collection of code as a program that we can run later and not have to type or copy and run a long line of code. This also becomes important when we want to run the code over and over again in the Monte Carlo simulation. This option rClass allows us to save it and export it to R if we want. Although in this video I'm going to focus primarily on Stata. It just defines the program as myreg and then we can run it later. What I'm going to do is I'm going to go through each of the steps of the program, clear it, and then run the program all at once so we can do the Monte Carlo simulation. But basically just know that what this command does is it creates a program, it names it, this option allows it to be exported to R, and that anything typed between this and when we type end is what makes up the program. But first I'm going to just do the steps of the program individually so you can follow along. The first bit of code just drops any observations or data that are currently in Stata. Obviously, if you just open Stata, it's not important, but it's a good sort of housekeeping thing to get in the habit of. The second step pertains to the simulation. What we do here is we just tell Stata that in the runs of the regression, we want there to be 100 observations. We're setting n equal to 100. You could set n to anything, but 100's a good number. 1,000 might even be better. But what it does is you just want to pick a number that accords to sort of the law of large numbers, and all those things we know about how if you just take one or two observations from a sample, you can get weird outliers. A larger sample washes out outliers and reflects the general pattern in the data. And then we need to set up what goes into our regression function. We know that x is a function of a constant term, but it's also a function of an error term and an x variable. And what this does is it tells Stata that we want to generate for 100 observations an error term u and x. Now Stata at this point doesn't know that u means error term and x means x. It doesn't really care. All we're telling it is, using some random process, generate u and generate x. And the default for Stata is that the mean of these is going to be 0 and the standard deviation is going to be 1. So it's using as a seed mean equal to 0, standard deviation equal to 1, normally distributed, and it'll use a random process to generate 100 observations of these variables. So if we go over to the variable window, we'll see that it's been populated by u and x, and we've told Stata we want it normally distributed with, and we can just do a quick check using a histogram to see how Stata's done. Okay, now obviously this is not perfectly normally distributed, but for 100 observations it's fairly good. And we know from 622, if we increase it to 1,000, 10,000, this distribution would get more and more normal. And we see that it's centered around 0. Okay, so we have u and x, but then we need to tell Stata what the process is by which we're going to generate y, or what is the population regression function. And so here we're just using the generate command, which you should know from 622, and just telling it that we're going to generate a new variable called y, and that it is a function of a constant term 2, x, and the sort of slope or the relationship between x and y is with the coefficient 3, and then there's that error term, that random or stochastic element. This is really important because remember, we're not modeling a deterministic phenomenon like as you might see in physics or the hard sciences. We're measuring social phenomenon which have this sort of random variation to them, so that's where the error term comes in. So as we do that, we'll see that we now have everything we need that's a variable for our regression function. We have y, we have x, we have u. And we can just sort of take a quick look at how well this data reflects our specified relationship by just doing a scatter plot. Okay, this is pretty good. Now, there's a strong linear pattern there that reflects the slope of 3. If we drew a line here um, for the y-axis, we would probably find that a line of best fit, or no, we definitely would find that a line of best fit intercepts that axis at 2. And of course, if we had a line of best fit, we'd see these points vary about the line. That's to be expected because we have that error term. They're not perfectly fitted to the line as we would, in something to do with gravity or velocity, for example. Okay. The next step is to just do a first run of our sample regression function. And here we're just doing, the basic Stata regression code. We're regressing y on x, and we're going to see from this one run how well the coefficients match up with what we specified in the population. So, okay, pretty darn close. We see 3.04 for beta 1, 1.83 for the constant term. That's not exactly right on, but of course, because we have that error term, there's going to be some variation around that sort of population regression line. So this is just a first run of the sample regression function on the data that we've created using the population regression function. Okay, now we're going to run this code, which just allows us to save for later our estimates of beta 1 and beta 0, and we can use them later in R. A scalar is just a fancy word for a number, a one. So this is just defining beta 0 as the coefficient for the constant term, and beta 1 is the coefficient for x. So what we'll actually do is we actually won't run this now because we're just doing it step by step, but we'll include this when we run the program because this code isn't really relevant to Stata so much, but what it does is it just saves these as objects that can be recalled later in R. But we'll include that when we run the whole program all at once. And then ends the program. So what I'm just going to do now is I'm just going to clear everything from Stata by typing clear all, and I am just going to run the whole program again from end all the way to defining the program because we'll need that for the simulation. And I've gone over all these steps. All I'm doing is just running it at once and saving all those steps as a program. So we're going to run the whole thing. So we'll see we've run the whole code, and it's just the Stata saved each step as a number. And so now we have a program defined as myreg, which we will need for the next step to actually do the simulations. So what we are going to do now is we are going to do 1,000 runs of what we just did. So basically we are going to run this entire code again 1,000 times, which is the same thing as using the population regression function, which is in our code, which uses an x and a y that are normally distributed with n equals 100, and generating a sample regression function by regressing y on x from those y's and x we generated earlier, and just doing it 1,000 times. So that's exactly what we're going to do, and it will take Stata a few seconds to do that. Okay, so now what we have is 1,000 beta zeros and 1,000 beta ones, 1,000 intercepts and 1,000 coefficients that have been generated by 1,000 runs of the sample regression function, which basically was just running that code 1,000 times. If we take a look at the data editor, yeah, 1,000 intercepts, beta 0, and 1,000 coefficients for x. And remember that we specified from our population regression function that beta 1 should be 3 and beta 0 should be 2. So we can already see some variation around that, which is to be expected. Now, obviously, just looking at 1,000 beta 0s and 1,000 beta 1s is not an efficient way to do that. So what we can actually do is just summarize. And we just do sum, and that just tells Stata, if we don't specify anything, that it's just going to summarize everything in the variables window. So this will give us the mean for beta 0 and beta 1 over 1,000 runs of the sample regression function. And given the law of large numbers, we know that these should hopefully approximate the population mean, which we've specified are 3 and 2. So let's see how close we are. We were very close. We see that for beta 0, the constant term, we're at 2.003, and we get to the third decimal place before there's any difference, and 3.002. Small standard deviation. So we can see that we have an unbiased estimation of the constant term, an unbiased estimation of the coefficient. And we'll get into this later, but the small standard deviation, ergo the small variance around the mean, tells us that these are not just unbiased estimators, they are efficient estimators. We can also get a sense for how closely they approximate the normal distribution. So let's look at a curve for the constant term. Pretty close. And I mean, imagine if you ran it less than 1,000 times, it would probably not as closely approximate the normal distribution. And if you ran it more and more times, maybe did 10,000 iterations, 1,000,000 iterations, Stata would take a while to do this, but you'd get closer and closer to a perfectly normal distribution. And for the coefficient on x, very close. You see the mean is around 3, which is exactly where it should be. That's the true population value that we specified in the population regression function. I'll allow you to do histograms on your own, and the subsequent video to this will take a look at what happens when you violate some assumptions with regards to linearity and also the error term.